Okay, so let's have a short start. So welcome back everyone. So we're glad to have Dimitri Wyss from Sorbonne University, Paris, and he will talk us about non-archimedean integrals on the Hitchin fibration.
Right. Thanks a lot for the introduction and the invitation to this conference and also the school last week. I appreciate it a lot. It certainly helps me to understand a bit what's going on with the talks this week. So my talk is sort of touches on a different subject a priori. I have two parts. The first one will be I'll try to explain a conjecture. Of Hausel-Thaddeus. It's about Hodge numbers of moduli spaces of Higgs bundle for groups SLN and PGLn. So their conjecture lives sort of entirely over so everything here will be over the complex numbers. And then in the second part, I will explain a proof. So that's our joint work with Groechenig or Ziegler. We give a proof of this conjecture. And the proof is somewhat indirect. So it's going to be sort of a purely geometric or topological question. And then we transfer it to a question first over finite fields. This is sort of sort of standard method by now. It uses very deep mathematics, but that certainly has been around for a while. And then we transfer it further, something which is less known, although not new either, to some p-adic field like QP, FQ, bracket T, non-archimedean local field. And then on these fields, we use a technique which is called the p-adic integration. Which is sort of an analytic tool coming from these fields. And so the way we use it is the same way as Batyrev uses this to show that birational Calabi-Yau's have the same Betti numbers or Hodge numbers. It's the same sort of idea, but since Batyrev, this hasn't really been used all that much in this direction. And in particular, what we do with, so I will explain sort of the technique in terms of how do you apply it to this conjecture, but it has some other applications too, which I don't have time to mention so much, but sort of, so I continue here. One aspect that appeared in the abstract is that it also gives this p-adic integration is an alternative to perverse sheaves. Or what is more precisely sometimes known as the support theorem. In the proof of the fundamental lemma. This was proved by and so this was quite a surprise. So we sort of avoid any homological techniques. Instead, we have some analytic tool that replaces this technical part of this proof. And so just to sort of advertise this a bit to the audience here, in particular, you get some non-archimedean or p-adic expression for the number of points of the compactified Jacobian, where C some singular is plane curve. this
And what is p-adic? This is just Q formula.
it's in terms of p-adic integral.
Like Tate in his thesis, right?
Yes. Yeah, same p-adic. So I will show you some, and so why might you care about this? So there are these conjectures of Oblomkov, Rasmussen, and Schende, which relate sort of the link associated to such a curve to the Hilbert schemes over this curve, and then the compactified Jacobian, together with some perverse filtration, it basically sees the cohomology of the Hilbert scheme. So in some sense, even though I have nothing to say about how one actually could use this, at least you could hope that you can use some p-adic techniques to look at
This is classical. p-adic or default integral is exactly, well known, is exactly the number of points of Jacobian, right? This is part of fundamental lemma, right?
if it's smooth.
They begin always with p-adic integral over some invariant orbit here, and then smooth, this is negotiable, right?
Yeah.
Compactified Jacobian requires new elliptic, something like this.
Yeah, but this is going to be different. It's not, you'll see, it's not the same. Right, so in the fundamental lemma, you integrate over orbits. Here we will, okay, it's different. Okay, but so let me start now just with the geometry of part one. What is this conjecture? So I'll fix now a smooth and projective curve, say over the complex numbers, the genus at least 2, write the trace C for the canonical bundle of the curve, and so the key definition is the one of a Higgs bundle. Pair in theta with E over the curve is a vector bundle, and theta from E to E tensor AC is twisted with O C linear endomorphism. So,
if you could just in the chalk, there's like a thicker chalk. That one's really faint.
oh,
Or just press harder.
Well, maybe just press hard.
yeah, maybe that's
What is case
We have the
the canonical sheet. Okay. So these Higgs bundles, they appear sort of all over mathematics. But if you have never seen them, I always like to sort of, it's a very naive viewpoint. You have your curve, minus 1, and then you have your, over some point, you have your bundle, you have some vector space over the point, and then your theta at that point, because you can trivialize this guy, it would just be some endomorphism. That vector space. So at the first look, it looks just like you're doing linear algebra, but relative to a curve. You're looking at matrices parameterized by your curve, and in some sense, this is how, at least for example, the fundamental lemma, how these things appear. Okay, so once you have these, you put them together in moduli spaces. So I will fix now also L over the curve. An auxiliary line bundle of some degree D. And then, as I said, for this conjecture, it will be important to look at SLN Higgs bundle. So this is what you would call a GLN Higgs bundle. And it's going to be sort of funny SLN version, so it's going to be the moduli space. So there's some technical term here, semi-stable. theta, so Higgs bundles E and theta, such with the following conditions. So first of all, the rank of E is n, and so this will be a Higgs bundle for GLN, and now we're going to impose the condition that the determinant of E should be isomorphic to this fixed line bounded head. So that sort of makes it into some kind of SLN bundle, and then also as for SLN the trace of theta onto this. And then there's modulo some equivalent relation like this. And this is the space we want to consider. So the geometry I'm going to actually need is not super intricate, so what this does. So just to remark why I put this L. So if L would be the trivial bundle of the curve, that would be honest. Sort of, it would be an honest SLN Higgs bundle. And but if I choose a line bundle of degree, this is the second case, the one more interesting, the degree coprime to n, then what one gets is some twisted version which is smooth. In this case, and then it's smooth. Quasi-projective, which is not the case here. You will have strictly semi-stable. So this is one space, and then there's going to be a second space for the Langlands dual group, which I denote by M PGLn, and this one will depend on degree, not on the line bundle, but on the degree. So it has some similar modular description, or also for this talk we can take a shortcut and just define it as the SLN space quotient out by some group, finite group, where gamma is the n torsion of the Jacobian of my curve. So these are line bundles whose n tensor power is trivial. If I take such a line bundle and I tensor my E, then it will still satisfy this condition, and this defines the n action. So this gamma acts only on the E part, not on the E. And it turns out that this is exactly the PGLn moduli. And so, how does one study such spaces? One tries, of course, to use this modular description and play around. So one thing you can do, and what comes up is this Hitchin fibration. And basically, the idea is that theta, so to such a bundle E theta, I think of theta as some sort of matrix locally. I can associate the characteristic polynomial of this matrix. Certainly locally, this is if I trivialize all the bundles, this is exactly what I get. And if I glue these together, I get a map to what we would call the Hitchin base. This is just an affine space, and it's so this will be the coefficients of my characteristic polynomial. And if you just glue things correctly together, what you see is that this is in sections of canonical bundle to the I runs from 2 to n. And so here I put 2 because I assume that the trace is 0. That will be the first coefficient. So let me call this chi S for SLN. And so you see that this map will only sort of work on the theta, so it factors through this quotient. So you get similarly a map here for the get these two maps. The Hitchin map, so Hitchin showed for SL2 that these are proper, and so these are, and then maybe Simpson showed that they're always proper. That is nice proper map, and you can actually use this to describe the whole space, at least generically. Very nice, and this is, I also want to mention this. So this is a spectral description. The space, which goes as follows. So if I give myself an element in this A, say A is a set of AIs, so it's a degree n polynomial, but with coefficients vary as you vary along the curve. But over each point of the curve, if you evaluate, you really get an honest degree n polynomial. And if you look at the roots of that degree n polynomial, this will live over your original curve n, and it gives you a ramified color degree n of the curve you started with.
It's a polynomial with values in the canonical.
Yes, yes, so exactly. So it lives in the total space of the canonical. And you can even suggestively write CA as really the set X. So you get this ramified cover, and
So should it be in the dual canonical?
no, it's the right.
That's right, because there are roots. Okay.
Yeah.
So it is symmetric.
Yeah, there's a better. I mean, the intuition is over every point you have endpoints. And what's the why is this interesting? So now this will be important later. So I noticed by a diamond inside A. So it will be the set of A such that this CA is smooth. So in general, it will not be smooth, but this is some. This inside A is open and dense. And so how does it go? So if I take some A in here, I can look at the Picard of this smooth spectral curve. And then there's a map called the norm map, which goes back to the Picard of the original curve, C. And because this is just the generic degree n map. And so it turns out that the SLN fiber of this point, it can be identified with the pre-image of the norm of the line bound of element.
So there's no, you just take tensor product of spaces sitting at all the points in the fiber. Is that
yeah, locally you do this. Yes, it's really local.
You got some prims, the corresponding prim and variety.
Yeah. Right. So what I would sort of stress it's the prim, but the prim would be the kernel of this map, and it will act on. It will act. Makes the fiber is a torsion of the prim. That is the correct geometric picture here. And so why am I telling you all of this? We're getting to the conjecture, but to motivate the conjecture, I state the theorem. Hausel and Thaddeus should motivate the conjecture. It says that so the over
What is approximately the year, if you remember?
It's early 2000s. 2004. Maybe, I'm not 100% sure, I admit. So over this generic locus, the fibrations over the fibrations for SLN and PGLn, so are torsors for dual abelian varieties. So what does it mean? So I take a point here, I take its fiber for S and its fiber for P. As I see, S here will be a torsor for the prim, and on the other side it's just the same thing, quotient by gamma. But as it turns out, the prim and the quotient by gamma are dual abelian varieties. That's what they discovered, and it's not particularly difficult calculation. What I don't say is that they also sort of, the torsor structure on both sides is also dual. So the complications, but morally this, and that was motivated by this SYZ mirror symmetry picture for Calabi-Yau, where your two mirrors should be fibered over a common base with special abundant vibrations which are dual generically. And so here there's some hyperkähler structure, and if you rotate correctly, you get exactly this. So this establishes, if you like, these two spaces, M SLN and then PGLn are sort of mirror dual. And so what they try to see is then if there is some other instances of mirror symmetry you can detect in these spaces, notably on the level of the Hodge numbers. So is there some relation to the Hodge numbers? And to state the conjecture is about this, so let me introduce the notation of the E polynomial. So this is just some notation. So for X over C, any variety, set E X. So it's a two-variable polynomial, and it's going to be the sum minus 1 to the I, so I Q. We're going to sum over the compactly supported, in general can be mixed Hodge numbers of my variety X, and P and Q keep track of the two filtrations. This some gadget. It's like it's some Euler characteristic, which makes it an additive invariant of your varieties. Actually, to state this, it's not entirely necessary. So, but it's a nice way to package these numbers. The conjecture now is that essentially these two varieties should not have symmetric but the same for several reasons, for two reasons. One is that this one is smooth and this one will have this orbifold kind of singularities. And this is also something that Batyrev independently sort of noticed, that he noticed this for toric varieties. If the dual happens to have quotient singularities, sort of the Hodge numbers didn't match. They were too small on the orbifold side, and you had to add some sort of stringy Hodge numbers. So you need to put a subset stringy here, and then you also see that this side sort of seems to depend on L, and it's only on the degree of L. So you should really also correct by some germ. This will be a germ. And okay, let me define more or less this gadget. I don't want to spend too much time to explain this germ. So for the main idea, it's not super important. But is stringy invariant, or in general. So E. So the stringy invariant is going to be a sum of elements in the group. There's going to be some correction term, this after a number, and then there's going to be smaller E polynomial. And basically, what I do is I take the SLN moduli space. The element gamma, it acts on the space. I take its invariant. Things will be fixed by this single element. Gamma is commutative, so gamma still acts. I take the E polynomial of this twisted sector of it. And so this alpha L, I don't want to say too much, just I say in words, this alpha L is a germ. It will induce on each of these parts some local system. And
just to double check, so
Yes.
they have the same characteristic polynomial, but the story is from S to P, from SL to P, right? This is exactly the connection. But still, they have the same characteristic polynomial, right? But the meaning
this
of
is not about
connection is different.
this is not about fibers. This is the global.
Not about Hitchin fibers.
It's the global space.
But still, the main problem is that just two different things: SL and PSL, right?
Yes. It could be PSL, and they're fibered over the same.
But you know, fibration, maybe you can calculate it after all. If you have such a theorem, maybe it will just somehow follow from the theorem. No,
The problem is this is only generic.
generic.
This is not over the whole.
Understandable.
The singular thing is. So there is this local system. So you should take homology, the values in this local system, not just the invariant. So it
So
picks
there is
up.
no diamond here. Yes, there is diamond here. There is no diamond.
There's no diamond yet, but this will come up, of course. Right. So the whole trick of the p-adic integration will be that we reduce it to the diamond.
In new symmetry, you flip the Hodge diamond,
Yes,
but you don't.
They don't here. There's
Same,
some.
everything is same. Yeah.
Yes, and there's some notes which heuristically explain. I guess for once they're not proper.
Mm-hmm.
One side, so and on the other, and they're hyperkähler. And so hyperkähler I think gives you some other symmetry in the Hodge.
Oh,
And so together,
No, this is about algebraic structures in both actually, right? So you mentioned something about Keller, but this is different, about sticky structure, right? Rather than about there's no Keller.
oh, this is yes. This is, but because the equality as opposed to symmetry.
What Losha is saying that if it is Keller, then of course you can expect the flip, right?
I didn't say anything about it.
Okay, so that's the conjecture, and it's kind of wide. So, but in general, we need to come up with something else. So the first step, which I don't want to explain too much, basically, Katz has this very nice theorem in an appendix of one of a paper of Hausel and Rodriguez-Villegas, which explains the relation between this E polynomial, which is an additive invariant, to what happens when you pass to a finite field. So basically, you can do everything on the finite field, and the conjecture would follow from the same statement. Over a finite field, or rather for the same statement for sufficiently many finite fields, FQ, where you replace the E polynomial with the number of points. Okay.
There's different motivic measure, right? This is
Exactly.
motivic
Yes.
measure, right?
And if it agrees on sufficiently many Qs.
We have three. Okay. And by the way, Katz uses virtual Hodge numbers.
Yeah,
right?
virtual Hodge numbers. Yes.
But you somehow in the definition you used regular.
No, it's also virtual.
Okay.
But actually, for the conjecture, there's no cancellation. They are pure. So you don't lose any information but sort of as you on the way you might.
And Katz imposes strong polynomial count condition, some kind of different stuff.
No, right.
You don't need this.
No, if you have strong polynomial count, then the count polynomial is the polynomial. Right. But if you have two varieties which have the same count for sufficiently many things, even if it's not polynomial, they have the
So
same.
you don't need this condition.
No. Just
I want to ask if there's a version of like conjecture for type outside type A, and if there's any like check for it.
right. So.
And of that theorem also.
Oh yes, that I should say. Yeah, that's very good. So this theorem, yes. So for general pairs, there's a similar pairs. Similar result.
General pairs means GG check complex.
Sorry. Yes. G check Langlands dual group. It's a similar result. Okay, right here. Non-archimedean. And then positive characteristic by Chen. Right. So this is fine. Yes, you always have this duality. But you don't have smooth moduli space. In general, the stacks. So here we really this twist is really something special. And you can do for SLM. There's some very recent paper by Batyrev who in some cases finds something. And I think whenever you can make this conjecture, our methods should prove the conjecture, but you have to work out the geometry. Anyway, so you replace it to a counting problem over finite fields, and now this counting problem we will attack with this p-adic integration. So part 2. If you have any other questions for part 1. Okay. So the main player is some notation. So F will be a finite extension of so it can be both. It can either be QP or FPT. So not in the local field. We have F. Inside of F, you have O of F. That would be the ring of integers. And you get back to the finite field. You go to the residue field, which I always will assume. FQ, just the residue field. So here you can think of ZP, if you like, or FP. Double bracket. And so what else do we need? So F, it has its absolute value. So you know just like this. From F, positive rational numbers. And we also need this R measure. Yes, the R measure. So on F in the addition, and you normalize it such that the ring of integers has volume 1. So just okay, should be a colloquial. Just
ZP, can we say ZP, the normalization.
Yes.
ZP, not QP.
ZP, yeah.
That's
O of
it is Z.
O of
not
F.
Q.
Oh, that's the ring.
Yeah, the ring of integers. Just to give you some idea, so you can write O of F just as a set, the disjoint union over elements in the residue field times, so this would be the maximal ideal. So you get that the volume of this, for this translation invariant, you get this Q times the R measure, the maximal ideal, so you get that the R measure, the maximal ideal would be, for example, 1 over Q. Okay. So And sort of all the volume computations you do, it's sort of you cut and paste and reduce the finite field, and so it's very combinatorial. It's nothing mysterious. Okay, so but now with this absolute value, f actually becomes it's a complete valued field, and so you can just define an f analytic manifold. F analytic manifold just as over the real number. Really analog, completely the same definition, locally charged inside f to the n, and you have the analytic gluing map and so on. So you get this notion of an F analytic manifold, and you also have a F analytic differential form. As over. And this is the way, okay, you can do it, and it turns out it's a very funny notion. It's not particularly deep, so every manifold is a union of balls. Or in this definition. But algebraically, it's non-trivial. You can do it. So this is the only instance we care about. So now x defined over the ring of integers is a smooth variety. Then Whale observed that this maybe I should say, okay, this will be the case you're interested in, and how should you think of this now? So you can look at the points, OF points of my variety, or this will be contained in, of course, I can also look at the F points of my variety. Same, and both will be so this will both be F analytic manifolds, just by smooth equations. So locally, I can write down charts for this. Let me also say that if X is proper, then you have here equality. X over OF. Right. You can extend every F. And here you have what is called the evaluation map, which you take an OF point and you restrict it to FQ, to the residue. So this is the picture. Now Whale noticed that this manifold of OF points, it comes with a natural measure induced from the Haar measure. To Whale. For the construction. So you write your variety X as a union of covered with open, Zariski open subvarieties such that the canonical bundle like Kx restricted to Ui is trivial. So I'm giving the construction of the measure. You can trivialize, so you get some differential forms, algebraic differential forms on Ui. And so on the intersection on Ui intersect with Uj, what happens is that you have omega I, of course, Fij, omega j, some function which lives in the invertible element. And now one thing that is different to real integration or real differential geometry is that the Haar measure, it still takes real values. It's still a real valued measure, not a p-adic valued measure. So you cannot integrate these differential forms, you integrate their absolute value. And in fact, since this is a unit, they have the same absolute value. And so if you cover your variety XOF with this chart and integrate locally these things, it will not depend on the choice you make. So what you get is
Theta disappears actually, right? Theta actually disappears, right? It will not reflect.
yeah.
Combinatorial, telecombinatorial.
Yeah, it will not at all. It's sort of. That's right. So what you get is some canonical measure.
No, theta k, sorry, k. Your k will disappear, right?
Like K.
Okay.
So get the canonical measure. On this manifold X left. Of course. Well, I mean, if it's something canonical, then one can certainly write down the volume what it computes. And this is also a theorem in which way. It's not terribly difficult to show that you have that, so sort of the integral over x of f with respect to this canonical measure, it will be the number of points of x over the residue field divided by q to the dimension of x. And in fact, the proof is sort of easy. You simply have for every point over the residue field that the measure of the inverse will just be 1 over q. And why is this true? Well, that's this little calculation I showed you there. Basically, because it's smooth, you can restrict yourself to x being affine space and take this point to be the origin. Then all the points that restrict to that will just be as many m to is maximal ideal to the n. So n is the dimension of x. And then you see exactly get 1 over 2. That's all there is to this theorem. So, okay, nothing's going on. But it's all saying everything is easy. But so now something interesting happens. This is when this is some sort of discrete space. On the left-hand side, it has some analytic structure. In particular, you have the following. So if y is inside x, not equal to x, closed, some sub-variety, then if I integrate with the canonical measure of x, the OF valued points, it's going to be a sub manifold of smaller dimension. And so that's easy. Strictly smaller dimension. Just that's what the real numbers. This is something you could not do on the right. And you just have points. And obviously you cannot remove any points.
He's getting really close to Batyrev now, right?
Batyrev.
Batyrev.
Yes. That's exactly what he used to prove this theorem. So now, in the tradition of this conference, I'll draw a picture. To draw a picture. So how are we going to use this sort of simple observation? So say you have some singular variety. My singular variety. And you want to, and this is over fq, and you want to count the number of points. So often, or in good situations, this singular variety will actually live in some total space. This would be our x, but over f, just everything over fq. It live in some space where x is smooth over fq, and this singular variety is a fiber of some length. So this would for us could be the Hitchin fibration. And the total thing is smooth. So now what can we do? I don't know, maybe colors. So this is FQ. So now let's just thicken the picture and go from FQ to FQ double bracket Q. So we add a dimension, so it becomes sort of thick. So this is the T direction. And so now in this space, if the total space is smooth, I can draw for every point here exactly the pre-image of this evaluation. It's going to be some sort of disk around each point.
Can you press a little harder? It's really hard to see.
Oh, green is not good. Right?
No, green was fine.
In general. Green is
Yes,
good.
yes, yes, yes.
Okay. This maybe.
Yellow can be better, but I don't have yellow.
So what I'm getting at, you have this you get this sort of p-adic tubular neighborhood of your thing. It will map down to some tubular disk here. So let me draw this disk a little bigger. This disk here. So inside here, if I deform constantly, so that would be in this direction, I don't do nothing. So for each of these fibers, I still get my singular thing. But as I move away from here, so everywhere here, the fiber will actually be smooth. It will look like. So the fiber of this will be something. I get something smooth. As I'm away from this fiber. And this is of smaller dimension. It's the locus where the map is singular. And so I throw away just this line, and I integrate over these fibers, remaining fibers. And then this theorem will tell me that what I get is just the number of points up to some factor of t. So I integrate for each point in here the fiber, this fiber, which sort of deform in the t direction.
You do it or something here to prove the existence of such deformations.
Yes, yes. So I assume.
So you did it, right?
Yeah. So in this module, so this would be the modular space of Higgs boundary. We know it's smooth.
Deformation again.
Yeah, we know it's smooth. It has singular fibers, but total space is smooth, so we can deform. No problem.
So, and this is FQ adjoint T, even if F was a p-adic.
No.
You could also. This is just that.
Yeah, then it would be just smooth. This is, in general, your situation, you might not be able to lift to OFF in characteristic 0. You can always lift to F. It's really, you just deform constantly.
Felix, you mentioned just to make it some more understandable.
Yeah.
So forget about Felix, just different story about Felix.
Okay, so this picture now explains you how you could, for example, I haven't said, so if you take a singular Hitchin fiber, I mentioned that is a compactified Jacobian. And so this procedure would give you a formula of the compactified, the number of points of the compactified Jacobian using this smooth p-adic Hitchin fibers, volumes of smooth p-adic Hitchin fibers. So now I want to go back to the original problem. This theorem will tell me how I deal with the number of points of the SLN side. So the second magic.
What you justify this count points on singular fibers is still okay. It gives you
Yes.
exactly the right thing. Like using this deformation argument.
Yes.
Right?
Yes. And now the second point is, eventually we're interested in the total number of points of the SLN space.
So that's just like analog of the Lebesgue measure statement, that if you remove something of measure 0, the integral doesn't change.
Yes. Yeah, it's only that. Okay. Together with the lifting, because this is Hausel-Thaddeus lemma. Smooth point. So now we control this guy, the left-hand side, sort of through this theorem. But the right-hand side has this orbifold singularity. And so the second amazing feature of p-adic integration, that it also deals with the orbifold singularities. This may be even more spectacular. So let me just write the theorem. So let now x over OF smooth, and gamma acting on x some finite group, finite, say abelian, it's not necessary, abelian, and maybe the action should be effective. Then one can construct similarly on okay, so let also u inside x be the locus, because where gamma acts free, and I will denote by m m the quotient of x. I got geometric quotient. No, not that. Quotient. And so I again want now to, so this will be the guy we want to integrate over. And if I would just take the OF points now of m, that would be singular. That would not be a manifold. So I will throw away some points. So I will take all the OF points, which generically, so generic here means I have this quotient u mod gamma, which is smooth, and I want that my generic point, so for each OF point I can restrict to the generic point, I want that this one lies in the smooth. So over F I have a smooth smooth F analytic.
Just repeat. No, I'm not asking to rewrite it here, but just repeat. So you're removing what? All singular points. Now you will stick to Banjisa, so to say, right?
Yes.
Hitchin fibration, right? And what? You remove codimension 1 of all singular points.
Right. So I could write it also as I take all of OF
no,
points.
Just spell it. Spell it, please. Yeah.
I take all OF points and I remove those which are in the complement of U, of the locus where things are.
Remove all singular whatever, right?
Yeah.
Fibers, singular points.
Yeah. But it's important, so there's some subtlety here, of course. So you remove points which are entirely singular. So in this picture, if this is the singularity, you could have a point which, so an OF point whose closed point lies in the singular locus, but then generically it goes into the smooth. You cannot throw these away. So somehow you still somehow see the singularity if you restrict, but generically it's
not clear because integration of codimension 1 will not influence.
Yeah, but
you can remove them too. Actually,
these don't have codimension 1. So the example would be take A1 and inside, so the singular locus would be 0, right, over O of F. Just to make this is somehow important.
Okay. If you have singularity and because of T, okay.
So what I want to consider is, so I want to consider OF minus the origin, as opposed to GM O of F. That would just be the unit. And you see, this still has full measure. This is
so you will exactly sharply remove this singular fiber,
yes.
But point cannot be removed. I mean, the image in Hitchin fibration.
Yes,
right?
yes. The restriction. Okay, so I have this. Okay, let me write here that one is analogous. As in the construction of Weil, one gets a canonical measure. Yes. On this space M. Oh, basically, you just take the canonical measure on X and you push it. And if there's some ramification of this, you will see the ramification. And the theorem, which is maybe partly is mostly due to the NF and the Z, and then we also did our part to adapt to the theorem. But now, if I compute the volume of this thing, it has a similar expression in terms of the special fiber, but it's not going to be the number of points. It's going to be number of points of, say, the inertia stack. Or you can write it out and you get just the same as we saw. So this some Q power minus W gamma is the number of points of X, fixed points by gamma. Gamma is the finite group, and this is an element. And I take the locus.
How can we get this gamma? What is gamma?
Gamma is the finite group acting on X.
Why we assume that X on X here? X is arbitrary manifold. X is so far it's arbitrary manifold.
No. I started with X with the action of the finite.
Curve, even the curve will be started with the curve.
No, that will. So X would be M.
Modular space.
M would be SLN, gamma X, and this would be.
Why you need gamma?
because I want the volume of the
Because
orbital.
of PSL,
PSL.
because of PSL part of the story, right?
Yes, yes,
Not
yes.
for SL, right?
No, not SL. PSL. Right. So these are orbifold singularities, and sort of the natural p-adic measure you put, it will compute for you the stringy value.
Yeah, this is Batyrev, right?
Batyrev, right? He used it already, and then F-losers really used. So it's really sort of.
It could be Batyrev, or maybe not Batyrev, someone, right?
Yeah, Batyrev. So it's, to me, this is up to this point.
And if a point has stabilizer, then you should it comes with a weight, which is 1 over the size.
You can do it this too. It doesn't change the count. It's this weird thing when you have a finite group actually.
It was his approach to sticky numbers, which are very unpleasant, but here they are nice actually.
Right.
Sticky numbers are very unpleasant.
Right. Yeah, you could write stacky count, but for the number of points, it doesn't change.
No stacks, no whatever.
No need for that, but you could. And so now, the conjecture reduces to show that if I integrate over the SLN space over O of F, my canonical measure, it has just to be the same as the integral over the PGLn. Some canonical measure. So there was this F, and so this gerb alpha n. So strictly speaking, there should be some function.
This is a trick, but why the motivic measure based on wave filtration, why it coincides with wave measure here? We have two different measures, then motivic measures, right? Well,
No, this is.
You begin with something based on wave filtration anyway, some kind of Hodge number, and then which is of course uniform.
Then you go to finite field.
Why you have the same measure? Why you have two measures? One is count points mod p, and the second are there some general theorems that they coincide. You have three measures: Hodge, then wave filtration, and the third one is exactly count points here. Why they coincide? Why they give the same?
Yeah, that's Katz's theorem.
Because but still you need strong polynomial count. For
No.
example.
No. If you have two varieties.
How these exotic Frobenius numbers can appear now? They can potentially appear in your business, but they will never appear, of course, in definitions through wave filtration or whatever. They will be just P, right? Why is it uniform in terms of P?
No, anything. The statement is this: if you have two complex varieties, and you have some spreading out, such that over.
Coincide at generic prime numbers or
Yes,
some,
it's generic prime numbers.
even with a clear knowledge, then Frobenius can highly non-trivial eigenvalues.
Yes, I'm saying if the number of points agree for sufficiently many prime numbers,
Then no need to assume that it's uniform.
no. It's a theorem. And then from finite fields you go to this. And so now what we will of course do, we pass to the Hitchin base, and we just compare the integrals fiber by fiber. And in fact we do the same trick here. So we don't take the whole base, but we would just take the nice part of the base, meaning I take O of F points, but I want generically to lie in F.
But they agree fiber by fiber.
Yes. So we show something. And so now, okay, I almost over time. Let me just. So now, at some point, one has to prove something. Now we only.
Then you can prove that the function capture Hodge numbers, right? Virtual Hodge numbers.
Yeah, that's
right?
yeah. So now we have to just compare the volumes fiber by fiber, and this is the following proposition, which sort of allows you to deal with. So now we have to deal with these abelian varieties. So these fibers will be abelian varieties, but which have bad reduction when I go modulo p. You get singular modulo p. And what you can do is you can use Néron model to replace this. And so this is the content of this theorem. So
Can you write harder?
yes, sorry, I try. Phi A to B be an isogeny of dual abelian varieties. such that so there's the kernel of phi is co-prime to the residue characteristic. So this should now just happen over the field, p-adic field, not the ring of integers. And so A and B are dual. And so I take omega B, a volume form.
Doesn't change zeta function, right? Isogenies don't change zeta, right?
Yeah, almost, right. But that's true if they would extend smoothly over all of them. So I take B, omega B, a volume form B. So the canonical one is of course trivial, but we always have essentially one unique such form, which is invariant under the action of B on itself. And you show that if I integrate now the absolute value of this form over the f points of B, it's going to be the same as if I pull back the form on A and integrate over, regardless of how these varieties reduce modulo.
I know it from my child who said the same. The zeta function is the same for isogenous abelian.
But it's not this.
It's not this.
No, because what you need is that the neuron model of these things have the same zeta function. And so there's.
But you consider generic P. What is the problem with neuron model? Yeah.
No. For each P, you have to check it for all possible Hitchin fibers. So you always have fibers with that reduction.
But still, if you reach in every fiber, you're afraid to choose P.
No. No, you first fix
because
P.
Fiber will be
Yeah, you first fix P and then. And so the reason is just the duality. So here we use something non-trivial, but from a completely different. It's duality for neuron models. So if I have dual abelian varieties, the neuron models are in some sense dual. And this proves to this. And then so you prove this for each fiber, ignoring this.
Questions for Dimitri? So that's the lemma.
F, right, so F would keep track. So here it doesn't enter. F will enter if it happens that, so this is a quotient. Right? So it could happen that this fiber has a rational and this one doesn't over F. So then you get 0 here, and it turns out F will guarantee that you also get 0. But if you have rational points in both fibers, the function is just 1.
So I think you said you had to prove it that you had sufficiently many primes.
Yes.
That's true. How have you proven that you had sufficiently many primes?
So you just start with your curve C, what you find over the complex numbers, and then you spread it out. This is some standard procedure. You find some algebra R, some finite type R algebra, such that C spreads out to something smooth, to a smooth relative curve over R. So here you might sort of, so it could be something like C, and then you invert a Z, sorry. So you spread it out to Z. And this could be something like Z, where you invert 3, maybe 2 and 3. You can invert some finite number of primes, the bad primes, and then you get something.
Nice to require more explanations. Abelian varieties are smooth abelian varieties, right?
Over F, yes, over QP.
So what? Still only finitely many will require neuron models and stuff like this. Normally they are smooth. They are only finitely many points of that reduction, right?
No. Because I will. So I look at a singular Hitchin fiber.
This is a lemma which has no logically speaking, no exact connection to what you did before. You use this lemma. Lemma is just about abelian varieties, right?
This.
Yeah. Am I right?
This is true in general. This is
absolutely. So then we have two smooth abelian varieties. Abelian varieties have good reductions everywhere, but no need to be careful about this particular GCD condition here because GCD1 condition, right? So for sufficient for almost all minus some finite set of points of that reduction, you will get it, right? So then it is pretty much classical stuff. Isogenous, right?
No, it's not because it's. I want the fix there. I cannot choose the residue characteristic.
But you're free to pick for this business. Free to pick generic prime numbers here. Why do you need to be so specific? With neural models?
I mean, yeah, I can. Right. So here the
In
kernel.
the beginning, it appeared that there are homogeneous spaces over anyway over something, right? And then for genic P, it means isomorphism. That's coincidence, right? But anyway,
We
we
explain
can talk.
that,
We can
yes.
talk.
Dimitri, can I just ask, I got the last one, did I understand that the main theorem that you wanted to explain was that you proved this conjecture without it? Okay.
Right. Yes. So it will reduce to this nice equality.
Okay, so you reduced it to, I see.
Because, right, so here, sort of this canonical measure takes care of the stringy. It's sort of all packaged in just the volume will just compute the stringy computation. But you don't see it anymore. It's very nicely packaged.
Stringy, we are eliminated absolutely because of this here.
Yes.
So we are not nothing like this.
So why should that, I mean, what's special to type A about that?
The special is that this guy is smooth. In general, so if I put here, as I said, if I put here the honest SLM state without the twist, it's just singular.
I see.
Then
you have
no
the, you
division
only have
also,
this
no,
twist in
no
type A,
division.
there's not a sort of obvious smoothing.
No, not for other groups. I mean, if you give me maybe some specific group, maybe it can come up.
What were you going to say? If it's singular, then what would
Then, I mean, this is still true if it's singular. The volumes will still be the same, but I don't have the interpretation at some number of points. You know, that needed to. But the volume, I can. That's also an interesting. The volume you can always compare. It's somehow good invariant, but you don't know what it tells you.
Okay, let's delay further discussion to the break and let's thank you again. And Kashima 4.